Okay, so I think we wait a couple minutes to have people connecting, and we are on time right now. So thank you, Neil, and welcome to the University of Maryland Center for Environmental Science. And we have a webinar series. The topic of this webinar series is assessing coastal risks and enhancing resiliency. I'm William Nardin, a faculty in HPL at AMSIS, and we are pleased to conduct the seminar series here. And the seminar will be recorded, and please submit your question at the chat function at the end of the seminar, or during just at the end, during the last 5-10 minutes of the seminar. And the link to download the webinar will be following like in a couple of days. And today's talk is by Neil Ganju, a research oceanographer at Woodsole Coastal and Marine Science Center. The title of Neil's seminar is Developing Standardized Geospatial Metrics for Salt Marsh Management and Restoration. Neil received his PhD at the University California, Davis in civil engineering, and in 2001, Neil began working for the USGS at the California Water Science Center on the San Francisco Bay Sediment Transport Project. In 2008, Neil moved to the Woodsole Coastal and Marine Science Center and began multiple projects throughout the northeast coast of US. Neil research projects include numerical modeling, numerical modeling development, field observation of hydrodynamics and water quality, wetland and coastal vulnerability assessment, geomorphic changes, and eutrophication. So I hope you will enjoy this seminar, and I will switch to Neil for his talk. Thank you very much.
Thank you, William. It's a pleasure to be here. I wish I was in Cambridge in person so I could see so many of my old friends. And actually, just a little history is about 10 years ago, I was at a meeting in Chincoteague, which was completely unrelated to salt marshes, but Don Cahoon and Glenn Guttensbergen were there and asked if I knew how to measure suspended sediment concentration accurately. And I said, yeah, that's something we do regularly. I can definitely do that. And they said, well, can you do it at Blackwater? Knowing nothing about Blackwater, I said, sure, we can try it out. And so that spring of 2011, I went down to Cambridge with Pat Dickhoot, who was a former UMSI's person there with Larry. And we went down there and instrumented a bunch of channels at Blackwater. And that's really what started this entire project. At that point, everything I was doing was inner shelf numerical modeling on sand ripples and things like that. Nothing to do with marsh sediment transport, which is what I had done in California. So it's interesting how these things started and how you kind of come back. So I'm very pleased to be part of this UMSI seminar series. So thank you for having me. And I want to acknowledge my co-authors, Farah Defne, Kate Ackerman, many others, including Matt Kerwin, who was there at that first deployment at Blackwater, as well as Sergio Fagarazzi and several other co-authors who've made all these metrics possible that we're going to be talking about. So many of you have seen this first slide several times, but it never hurts to go over it again. We like to think of sediment budgets to salt marshes as much like a bank budget. So you have withdrawals of sediment, you have deposits of sediment, and the implication is that that net balance of that budget tells you if a marsh is in stability or not. It's obviously really complicated to measure these individual withdrawals and deposits. You'd need many kinds of different instrumentation to get at those quantities and temporal fluctuations, but they're important. They determine the salt marsh budget, and you need that budget to be positive in order for a marsh to respond as a whole to sea level rise. And so, for example, you see this plot on the bottom right by Sergio Fagarazzi and others, a series of model simulations showing how marshes respond to sediment supply and sea level rise, showing that there's a very narrow parameter space when marshes are in equilibrium, but most of the time they're either expanding or eroding in response to those two external factors. So to get at that budget, what we've done over the past 10 years is measure the sediment flux coming in and out of tidal channels that drain entire marsh complexes. with the idea being that you can integrate all of those small withdrawals and deposits by measuring flux in and out of a control volume of a marsh. So the question that we had early on in the study, after that first Blackwater study where we compared two sites, was can we infer the stability of a wetland by its sediment budget? And does it link with other metrics? So we did those measurements, 8 locations across the nation. And in our 2017 paper, we synthesized those to show how the sediment budget was related to the unvegetated vegetated marsh ratio. And that's an aerial imagery based metric that basically just divides the area of unvegetated marsh. So that's ponds, channels, mudflats, et cetera, divided by the vegetated plain. And so at a low UVVR, that indicates stability where the marsh is intact and the sediment budget is close to neutral. And then at a high UVVR, the marsh is deteriorating, open water is expanding, marsh is being lost, and the sediment budget is negative. One of the interesting points from this study was that every site that we studied across the nation was in a sediment deficit when you account for sea level rise on top of that. The most stable site was actually right there down the street from you at Fishing Bay, off the Transquaking River, one of the sites that we compared against Blackwater that had a large external sediment supply from a turbidity maximum in the Transquaking River, which was really interesting. Nonetheless, what we found in that study was there's a tipping point somewhere around 0.1 where a marsh crosses from a surplus to a deficit. So keep that number in mind because it's gonna come up again later. Excuse me. So the other thing we could do is calculate a sediment-based lifespan. And so the idea there was you take the mass of sediment in the marsh, you divide it by the sediment budget, and that's basically mass divided by mass per unit time, and you end up with a time scale. And this was Sergio's idea to compute this lifespan estimate. And basically what you need to do to get that is you need the UVVR, this unvegetated vegetated marsh ratio, you need the elevation of the marsh plain, you need a sea level rise estimate, and you need some bulk density estimate. The nice thing about that calculation then is you can kind of fine tune it to your site for those different variables to compute lifespan. And what that study showed, again, was the highest lifespan marsh was the Fishing Bay site off the Transquaking, with a lifespan of something like several thousand years under present rates of sea level rise, which is important to consider. And then Blackwater down here at 84 years was the least stable site. And to be fair to my co-authors, I should be calling this Fogarazzi versus Kerwin because this was Sergio's idea and the UVVR was Matt's idea early on. So this is the Fogarazzi-Kerwin curve is what we can call that from here on out. So one thing about the UVVR that has been backed up by several studies during that same time and after that time is that this UVVR appears to be quite robust when compared with other studies. So on the left here is a modeling paper by Andrea De Alpos, Marco Morani, and this is a coupled eco-geomorphic model that had vegetation in it, has sediment transport, has hydrodynamics, and vegetation response to hydrodynamics. And in their study, they also did, again, this is that same parameter space of sea level rise on the y-axis, sediment on the x-axis. And under their highest sediment supply, lowest sea level rise case, they came to a UVVR, which they computed after the fact in response to our work, of 0.13. So again, this is very close to that 0.1 value I was talking about a minute ago, and then an unstable value up here with high sea level rise and low concentration of 0.35. On the right here is the 2016 paper from Giulia Mariotti, and this different model, but similar processes accounting for open water expansion, and again, sea level rise on the y-axis and sediment supply on the x-axis. And I've picked a tide range case here, which is what this R is. This is the highest tide range case of 2 meters. And he has other cases with lower tide ranges, but I picked this one because what it shows you is that even if you're a macro or a mesotidal marsh, but a large tide rate marsh, under present sea level rise rates, which are in this 3 millimeter and upward area, and low sediment supply, you're in this pond collapse regime, which is essentially the UVVR expanding. So an increase in UVVR and expansion of ponds. So there's a lot of evidence behind this parameter as being a proxy for stability. And then in 2020, we did a synthesis comparing the Mars metrics from Kenny Raposa and Kristen Watson's paper. And what we did was a decadal change in UVVR using NAIP imagery and compared that to the present static estimate of UVVR. So basically the y-axis here is the change. I think it was from, it depended on which years of imagery you had, but it was the most recent 10-year change we could do. And then on the x-axis is the present day UVBR. And what you can see is below 0.15, which is this dashed line, there's a fair bit of noise, but above that, once you cross a certain threshold of UVBR, you get a rapid change in UVBR. So basically, it's this runaway expansion, which has been pointed out in several papers, especially by Julia Mariotti, where once you get to a certain threshold of open water, you can rapidly expand in absence of external sediment supply. So there's a lot of evidence now showing that this metric is useful. It's consistent across observational and modeling studies. So we consider it to be pretty robust. And regardless of whether or not it's a precise indicator, the fact of the matter is, if you want to understand the services of your marsh, whether it's from vegetative cover, sequestering carbon, whether it's from wave attenuation by vegetation, whether it's by habitat use by certain species, you need to know how much of your marsh plain is vegetated. That's a pretty simple metric that you need anyway. So we consider this to be something that's essential and necessary from many standpoints. So just to give you a feel for what this means on the ground, here's a marsh unit, is what we call these things. This is a marsh unit from Great South Bay, New York. And you can see some open water ponding. There's a little bit of development here. So what we do is we take the National Wetlands Inventory, emergent wetlands as a first mask, and we use the NAIP imagery, which is usually better than a meter in modern days. And with that, you can do a classification into 32 bins, and then the operator, in this case, Kate and Zafir, have developed a workflow for this. They basically go in and select which ones are vegetated and which ones are unvegetated. And that gives you this 1 meter mask of unvegetated and vegetated data. They also use the elevation, which is usually from LiDAR, as another classification bin, which helps you identify what's vegetated and not vegetated. And then we use the LiDAR to also delineate marsh units. So these are like hydrologic units, as you would do in watershed studies, basically constraining the topography of the marsh into individual units, which is useful from a management point of view. And then you can aggregate that 1 meter UVBR to compute a UVBR over each unit. And so what you see in this one is a very high UVBR marsh unit right in the middle of the marsh, and lower UVBR going outside. And I can just back up to show you what that unit looks like. If you back out, you can see it's this area with a lot of open water ponding. And so what we do is we calculate the UVBR on these units. We get the elevation from the best available data set, whether it's LiDAR or something else. We calculate the elevations for the vegetated area, the unvegetated area. Sometimes we'll extract model output if there's hydrodynamic models that have things like tide range, sediment supply, salinity, exposure. We can pull those variables and apply them in these marsh units as well. And just for information, we've kind of tuned the watershed delineation part to give us a consistent size of marsh units that averages about 30,000 square meters, or if it was a square, 170 by 170 meters. So we've done this on several scales, but here are the 4 estuaries where we did it in our 2020 paper. So I'm showing elevation on the left and UVBR on the right. And so this is Plum Island Estuary in the northeast. This is Cape Cod National Seashore. This is Great South Bay Fire Island. And this is Assateague Island, Chincoteague Bay. And we've also done this for the state of New York. We're currently doing the state of Massachusetts. We'll be doing Connecticut soon, and we're doing the entire Chesapeake Bay as well. And so each one of these is showing you a marsh unit, as I showed in that prior slide. And these range from something like, I think Cape Cod had maybe 500 marsh units or so, and then Assateague had 4,000. So depending on the size, you get quite a variety of numbers. But the idea is that you're now kind of separating the marsh into individual units so you can compare these metrics. And just to show you where we're at in the Chesapeake, this is the work that Kate is doing right now. And we finished the regions that are highlighted. And one of the things we're doing, which I'll show in a second, is we are comparing elevation from the USGS coastal elevation data set and elevation that's been corrected using vegetation metrics by Kevin Buffington and Joel Carr. We used, again, do the UVBR with NAIP and Landsat, which I'll be talking about. We're looking into these other metrics that have been proposed, skewness, percent, 1/3. I won't be showing those today, but I have looked at those. And then other stuff we're developing for the Chesapeake includes wave thrust on marsh edges, the tide range, maximum nuisance flooding, inundation, and other things. And then Grace Molino has recently published a marsh forest slope analysis to look at potential marsh migration in the forest. And she's working now on her PhD in Matt Kerwin's group, and we're looking forward to more of those results to integrate as well. So just to show you what those results look like when you synthesize them. So this is now the data from those 4 regions. Each one of these dots represents a marsh unit. And so when we plotted these up and then fit a curve to them, they all had similar behavior, but you can see they're offset. And the first thing that comes to mind is, well, these marshes have very different tide ranges. Plum Island has almost a 3-meter tide range, and Chincoteague has a tide range as small as 10 centimeters in the middle of the bay. So yeah, you know, we see this consistent pattern. When you bin average, it becomes a little clearer. But what we wanted to do is demean them and detide them to see if they collapse. So we basically subtract out the mean elevation of the entire complex and then divide it by the tide range. And what happens is you see these actually really collapse down. And so now these are the bin averages of the demeaned detided elevation versus UVVR. And what you see is for those 4 estuaries, you know, you have this consistent decrease in UVVR as you get higher in the tide frame, but the curves all kind of collapse at a UVVR of 0.1. And what this is telling you is that in a given complex, if you're below the mean elevation of the entire complex, you tend to be laterally unstable. If you're above that elevation threshold, you are laterally stable. And that's kind of an interesting finding. When we do that in the Chesapeake, we find the exact same thing. So this is data that's still in the works, but this is actually showing you the coastal elevation data set from the USGS, which is essentially LIDAR. And this is showing you that same data that's been corrected for vegetation effects on the LIDAR. And so what you can see is the elevation range kind of shrinks, but the behavior is almost identical. And this dashed line here is the mean elevation, and you can see it crossing at 0.1 as well for both of these data sets. So there's a lot of kind of consistency and coherence in these patterns that point to lateral instability matching vertical type, where you are in the vertical frame, which to all of us who work in salt marshes, that's not surprising. We know that the lower you are in the tide frame, the more exposed you are to destructive processes, the higher you are, the less exposed. So this is pretty intuitive, but it's nice to quantify this across larger scales and have some actual evidence to back it up. To me, then, the bigger question is, how do we use this relationship to actually inform management and restoration? So to me, you know, you see these consistent patterns. My question would be, well, what happens when you're not consistent with this pattern, when you might be high UVVR and high elevation, or low UVVR and low elevation? So something I came up with recently was a decision matrix of how to actually prioritize restoration using these information that we've all been collecting for years. We've been working with elevation data, SCTs for years, and now we're starting to work with the UVR. The question is, how can you bring them together to actually give actionable information? And so one concept I've been working on is picking the areas that have kind of opposite behavior. So in green are stable, right? So your high elevation, low UVVR, and let's say you're a marsh unit that's in this parameter space and you're a coastal manager. Presumably you would leave it be. You wouldn't need to do any action on it. If it's private land, and you're a coastal manager, you may try to acquire that land in order to preserve it for either carbon sequestration, wave attenuation, or habitat provision for endangered species or threatened animals. Now, if you are a low elevation marsh with a very high UVVR, then maybe it's not worth any investment because you are so unstable. Maybe you just want to abandon that parcel. The more interesting are the other 2 cases. So if you're a low elevation marsh, so you're very low in the tide frame, but you're internally stable. The marsh plane is consistent. There isn't any open water ponding. The sediment budget is therefore implicitly positive. You might want to institute a monitoring program to keep track of that parcel, as it's obviously stable, but you want to make sure it doesn't cross the threshold. On the other hand, if you're a high elevation marsh and you have lots of open water ponding or you have expansion, now you need to start thinking about migration corridors upland of that. Perhaps runneling to drain off some of the standing water is an option. If you have ponds that are not standing water, or I guess open water pans that are not filled with standing water, maybe you want to start planting, or maybe you want to start filling those ponds with sediment if you have a local sediment supply. So an example of what this looks like, and this is actually from New York. Basically, I just pulled data points out of those relationships that fit into these boxes. And so here's a high elevation marsh with a low UVVR that's next to a Coast Guard station. So if this is not public already, look into acquiring it. Here's a low elevation marsh, low UVVR adjacent to a large tidal channel. And you can actually see there's upland forest here. So this is an area you'd want to monitor closely. Here is a back barrier marsh that's high elevation, but also high UVVR. Here it's interesting because you might want to make sure that the overwash migration, that you're not building dunes, fake dunes on the open coast that don't allow sediment to fill those ponds during extreme events. And then here's a really degraded, low elevation, high UVVR marsh. And I think any one of us as a coastal manager would look at that and know that you have to do something proactively, either abandon it or try to fill in those ponds. But in this case, the UVVR is well over 1 and certainly a candidate for abandonment. The other metric I want to talk about is the lifespan. Now, this is something we proposed in the 2017 paper. We expanded a little bit in the 2020 paper where we detailed the calculation a little more. And basically what you're doing is you're using the UVVR sediment budget relationship to estimate a budget for each marsh unit. Certainly there's a lot of uncertainty in that estimate, but it's the best we have if you want to do this over large scales. And then at the same time, you calculate the sediment mass in a marsh unit. So you take the elevation above sea level of the marsh plain, the vegetated part of the marsh plain, the area of that vegetated marsh plain, and some dry bulk density. So for simplicity, we just use the average from Jim Morris's paper of all of his sites. But presumably, if you had on the ground detailed density, you could actually fine tune this and do it correctly over every single unit if you had marsh density estimates. That gives you the marsh mass. And then you simply divide that mass by the sediment budget multiplied by the area to get a lifespan. So for example, for Assateague Chincoteague, that's what this looks like. So you can see this very clear gradient where in the south, where you have very intact high elevation marshes, the lifespans are quite long. Some of the mainland marshes here are falling apart, have lower lifespans. Up here near Trap Creek, Newport Bay, where you have quite a large nutrient source and some marsh degradation, you have very short lifespans. And then the back barrier, you can see this pattern of higher lifespan next to the barrier and then lower lifespan as you're moving closer to the estuary. And it's a pretty intuitive metric. So when you zoom in on a couple areas with low lifespan, you can see these are units that have very degraded marsh plains. They're very close to sea level. They even have some edge erosion happening here. So it's a very intuitive metric that can be used to actually give you a quantitative estimate of how long your marsh unit has left. Now, one thing we haven't done is tested this anywhere. You would need to do a hindcast or a forecast. So just the other day, I remembered these images because Matt Whitbeck at Chesapeake National Wildlife Refuge sent the full data set of these imagery to Giulio Mariotti. And I decided, well, maybe I should just have a look at the images that are online and see if I can do anything with this. So you have this topo map from 42, which you can look at. You have a 1938 photo. I digitized both of these in MATLAB and computed the UVVR and came up with pretty close numbers. So something like, 0.8, an average of 0.82, right? So I have a UVVR from, 1940 or so. So let's call that UVVR at time 0. And then what I assumed is that the elevation back then is the present day elevation plus what sea level rise took away. So you're basically assuming the marsh plain didn't move and sea level rise has come up to bring it to where it is now, which is pretty conservative, right? Because what you would have imagined happened was as sea level rose, the marsh plain was trying to keep up over all these years. So this is a very conservative estimate where you're giving the marsh a real fighting chance. You're saying back then it was super high relative to sea level. So you have we use the elevation from present day from that lean corrected data of 17 centimeters. So that gives you an E0 back then of about 0.4, 24 centimeters. So basically 80 years times 3 millimeters per year, which again is pretty conservative, right, for the Chesapeake Bay region. So we have these variables and there's your sea level rise and your time frame. And when you do the lifespan calculation, you get a lifespan not exceeding 87 years. If you use a bigger UVVR, so if you were, for example, to use this UVVR, you would get even shorter lifespan. If you were to not assume this very conservative elevation threshold, you would get a shorter lifespan. And if you lowered the density from 373, which is probably pretty high for Blackwater, you would also get a shorter lifespan. So this is a super conservative estimate. And as we all know, this central part of Blackwater is now completely open water. And the prediction would have said that it would be gone by 2025. So as a preliminary test of how this works with hindcasting, it certainly seems somewhat realistic and a good proxy for lifespan. Now, how you could actually use this then, again, this is to that management aspect. Here is if you basically compute lifespan, which is what these contours are, as a function of UVVR and elevation above sea level, you can kind of look at trade-offs between how you would invest in either reducing open water area or building elevation or both. So let's say you have a marsh unit that has a UVVR about 0.28, elevation of about 6 centimeters, and you need to somehow extend the lifespan from 40 years to 100 years. So what should we aim for? So let's say you want to go at a 100-year time span, and what it shows you is if you just add sediment and build the elevation without actually filling in any open water or unvegetated marsh plain, you need 10 centimeters of sediment. So you're going from basically 7 centimeters out to 17 centimeters to get to 100 years. Alternatively, if you were to runnel those open water areas, let's say they were ponds, and you runnel them and you drain off the water and you institute some kind of planting program, you can reduce your UVVR down to 0.14 and get to 100 years. Or alternatively, you can do both and reduce UVVR and increase elevation at the same time to get the same lifespan. So this is one of those kind of structured decision-making concepts which I've just learned about recently, but this is a way to sort of evaluate how much money you want to spend on different techniques to increase the lifespan of your marsh unit. So then finally, the last thing I wanted to talk about is doing this on wide national scales. So everything I've just shown you is technically possible globally with satellite data. So what we've done is we've partnered with Brady Cuvion, who's at the Wetland Center in Louisiana, USGS, and we've calibrated Landsat data with the NAIP imagery to generate a UVVR on a 30-meter pixel for the entire nation. And so those data from 2014 to 2018, annual data that we are serving up annually, but also composited for a 5-year average, along with the standard deviation, is complete, and it's finishing USGS review and will be published. This is what it looks like just for Plum Island, just showing you this is that 1 meter UVVR product, and then it gets aggregated for the UVR pixel in Landsat. And when you go around the country and look at it, it looks really good. So an area that I started working in San Francisco Bay, you have some nice patterns that show up where you can see in green marshes that are holding together, and then in red areas that are falling apart. Here's the Mississippi Birdfoot Delta. You can see the open water conversion near the Delta, and then more consistent marsh plain closer to the Atchafalaya. And then it turns out that it actually works well for mangroves too. So for example, there were a couple of dieback events in the Everglades near Flamingo that the UVVR actually captured year to year with the Landsat data, and we've been looking at that as well. Now, the beauty of this is if you have a 30-meter UVVR product and good elevation data, which is variable across the nation, but for a first cut, you can use the Coastal National Elevation Data Set. And if you use that along with downscaled sea level rise projections for the nation, you could actually get marsh lifespan nationally under multiple sea level rise scenarios, which is something we're looking to do. And the beauty is that you can update those products as new things come in. So you get new satellite data, you can update the UVVR, you get better lidar elevation, you can update your elevation estimates, and then you can actually test the accuracy. So if you have a marsh unit that the prediction says the lifespan is 10 years, well, the next update you do in 10 years, you should see that that marsh unit's lifespan has been reduced to 0. Otherwise, this prediction is not working. So that's something we're looking to do as well. So basically, sediment budgets are, in my mind, still the gold standard for getting a sediment, an idea of stability. But as we all know, technically, it's really difficult. It takes a lot of work. It took us, many years to get 7 sites, and we had to pull another one from the literature. So bringing in the geospatial aspect from remote sensing has a lot of benefits. You can formalize things, you can update with modern satellites, and clearly a lot of these things are being backed up by on-the-ground studies. And then in my mind, the lifespan is really the thing we need. That's what managers need to figure out where to make investments, how much time they have before they need to acquire more landward parcels, before they need to make plans for certain species that can't use the marsh anymore once it falls below a certain elevation threshold. And then the fact that the lifespan is linking the vertical and lateral is what makes it really attractive to me. And then again, it is objective. You can reproduce it and it's testable with newer data. And all these data that I've shown are actually served online. The Landsat UVVR will be online shortly, hopefully in the next couple months. You can find all of this stuff at the US Coastal Wetland Synthesis GeoNarrative that Zafir's put together. You can also hit it with your smartphone to get it there. And I think that's it. So thanks for your attention and thank you for the time.
Thank you, Neil. So it was really interesting. And I think we have already like 3 or 4 questions.
Would you like me to stop sharing the screen or keep it up?
No, we can keep it up, like it's okay. So I think it was a while ago, like Sandy Hertz, she asked, can the abandon option be considered beyond, just 1 second left, beyond hope for recovery? Or should we consider this location for dredging material placement and reconstruction of marshes?
Yeah, that's a good question. You know, initially, when I made that decision matrix, it said abandon or sediment placement. And I think, you know, that's I've had this conversation with managers where, you know, as an engineer, I try to be very blunt and broad with my thoughts. And they've pointed out that, you know, on the ground locally, it always depends on where that parcel is, where it is relative to a dredging project, relative to whose land it is, to know what we can really do. And so I think you're exactly right. In this case, you know, if this is next to, let's say, the intercoastal waterway, for example, which it's not, but let's say it was, and there's regular dredging of the waterway, certainly, you know, filling in those ponds is not the worst thing you could do if there's a local sediment supply that isn't interfering with the rest of the sediment budget, which is a whole nother question, specifically for the intercoastal, for example. But I think in general, on the ground decisions about where there's a local sediment source that can be used to buy some time is certainly a valid approach. Absolutely.
Thank you. So another question by Rachel Isks is, can you explain the negative effect of open water ponding on salt marshes? Why is open water and low tide a reason to abandon a site?
Sure. I guess the idea is it's a question of benefits. So it's a question of habitat provision, carbon sequestration, and wave attenuation. So those are the ecosystem services that we expect from marshes. So for example, so you can see on these 2 units here on the right, the upper unit is behind Fire Island, which has substantial plover habitat. And one of the things the plovers use is they forage back in those back barrier marsh areas sometimes, or they mostly nest on the beach, but that habitat behind is part of that geomorphic continuum. So if you want to preserve that habitat for plovers, ostensibly you need to maintain the salt marsh behind it as well. So that's one aspect of it. In terms of wave attenuation, you know, in many locations across the country now, restoring salt marshes along the fringes of estuaries in order to kind of maintain shoreline position and attenuate waves is an ongoing process. So, you know, this marsh unit here, for example, on the bottom right, if this was fringing, let's say, a road or a bridge or something, and you're trying to dampen the effect of storm waves, this marsh unit is not going to do it very well. Whereas if it was vegetated, it would do it much better. So it's kind of a function of those ecosystem services that marshes provide. Having said that, there are many places in the country, specifically San Francisco Bay, where shallow open water habitat is actually a restoration target. So there are socioeconomic benefits of shallow water habitat that should not be ignored in terms of productivity and fisheries habitat. So, you know, again, this is where the socioeconomic part comes into play, and that's beyond my expertise and knowledge, but that's the short answer, I guess.
Yeah, I think it's very clear. And so I think connected with that question, we have another question from David Blatt saying, from management perspective, should the UVVR results be interpreted differently if the marsh is impounded, restricted versus open unrestricted?
That's a great question. You know, my colleagues in our office, Kevin Kroger and Megan Eagle, have been working on the degradation of restricted wetlands and how to restore elevation capital when those restrictions are opened. I haven't explored that yet. My sense is that it's going to kind of depend on the location, because what I know so far is a lot of the restricted wetlands, specifically because you're restricting, saltwater, there's a lot of Phragmites. And from my understanding, or at least what I've seen, here in Cape Cod, Phragmites tends to build a pretty dense stand and doesn't have a lot of open water in it. And so the UVVR is actually quite low. So that's a really great question. I think that's where mapping these variables along with species composition becomes important, because my guess is that a lot of restricted wetlands that have a lot of Phragmites are going to have very low UVVRs, yet are going to be considered undesirable, and also from a vertical perspective, somewhat unstable because they are lower in the tidal frame because of those restricted tides. So I hope that gets to the question. That's a great question that we need to explore a little more in depth.
Okay, thank you. So prepare yourself, there are a lot of questions. So I think we will go until noon. So, but I think, okay, I will go with other few, and then you let me know if you feel like you have to stop. So so this is from Laurie Stever. How would you use or adapt those methods to inform marsh design for restoration and creation projects?
Yeah, I think one way is to use elevation and the UVVR in combination, kind of like I was showing um, on this plot, and not necessarily just for the lifespan calculation, but knowing that we have stability, lateral stability somewhere below 0.15, and knowing where you are presently in your elevation distributions across the marsh, and kind of using those in tandem to say, okay, let's say our UVVR is something, like 0.5. You're not going to basically be able to reduce that without, adding sediment to a certain elevation so the vegetation can actually take hold in those areas. So it's got to be a combination of knowing how much you want to reduce the UVVR, which to me, if you're going to put the effort in, you should try to get it to 0.15, because the evidence from several studies, not just ours, shows that 0.15 is kind of that tipping point. And then knowing what elevation supports the species that you're aiming for. As folks have mentioned, like you don't want to restore to an elevation that favors Phragmites, for example. So I think using those in combination to then calculate how much sediment you're actually going to need, for example, if that's what you're doing, and then maybe using it in tandem with this lifespan calculation and how long you expect the project to last, is one way to do it.
Okay. So next question is from Cindy Palinkas. So she asked, I was wondering how you communicate uncertainty with the managers that might use some of these metrics.
Yeah, that's a great question. I guess that was kind of my attempt with this matrix. Was matrix here? Yeah, that was kind of my attempt with this matrix, is that, there is a lot of uncertainty about what the UVVR means if you are in certain regions, right? So for example, we know that the UVVR doesn't work if you're somewhere like the Wax Lake Delta, where there's a new source of sediment, well, not a new source, but a huge source of sediment that's actively creating mudflat, that's actively in the process of vegetating, right? Wax Lake Delta has a really high UVVR, but the sediment supply is huge. So it's in a different parameter space, for example. We know that maybe in some high latitude marshes that have a lot of natural open water ponding, the UVVR might not be the best metric. But the idea here is if you have elevation data and UVVR data, there's not a lot of uncertainty in this matrix. So if your UVVR is 1 and your elevation is sea level, to me, there's no uncertainty there. You have to make a decision about what you're going to do. If you have a local source of sediment, use it. If you don't, abandon it. If you're high elevation and your UVVR is below that tipping point, there's nothing to be done other than paying attention to making sure it stays public or it doesn't get developed. So that's my attempt to evaluate uncertainty. And I'll be frank, I'm bad at evaluating uncertainty, again, because I'm an engineer and a numerical modeler by training. So everything's always correct or within a safety factor of 1.6. So, I'll admit that's a big problem I have, and I don't know how to communicate it very well. And I took a structured decision-making class to get better at it. So this was my attempt of what I learned in that class. And I'm open to suggestions anytime.
Good, good. So another question from Larry, I think is also related to the sediment word. Like, could you build sediment supply into the lifespan estimate by correcting for additions to elevation over time?
Yeah, you can. That's a great question. So you would do that. Where did the equation go? Yeah, so basically, yeah, so what you can build in, and I didn't show it here, but it's in the 2020 paper. You can modify inside the sediment budget, you can add different sea level rise rates, for example, which is basically the opposite of what Larry is asking. So that's imposing a new deficit. So if you wanted to do additions through time, you could also add that, but you'd have to do it in sort of punctuated intervals. I don't know if there's any way. I mean, I guess you could make a function in here as a function of time that adds sediment, just as you would take away sediment through a sea level rise deficit. So certainly that's something you could do, and that's an interesting idea. And that's very much a structured decision-making type approach where you add the actions in and then evaluate how much you have to tweak year to year. So yeah, it's a great idea.
Okay, so next question is from Rally Hood. So what's the role of stratigraphy substrate characteristics below the marsh in determining marsh erosion rates? For example, like a clay substrate like we see over here on the eastern shore versus more sandy substrate elsewhere.
Yeah, that's, as far as I know, that's still a pretty big unknown. I don't know if there's enough of us working on that. I know down at LSU, I want to say it's Naveed was working on such measurements. I think Giulio Mariotti has been applying some methods. I personally don't know the role. You know, my original training was in sediment transport, cohesive sediment transport. So certainly from just a hydrodynamic shear stress perspective, we have some information about how those things work, though, again, our uncertainty is 60 to 100%. You know, in terms of actual marsh loss, you know, there's basically the two mechanisms of edge erosion and then open water expansion, internal deterioration. So the edge erosion part is clearly linked with the density of the substrate below the marsh plane. So what's getting, you know, attacked by the waves, how dense that biomass matrix is, as well as what that substrate is, clay versus sandier, influences that erosion rate probably. Again, there's not a ton of data on that. From an internal deterioration perspective, there's a lot of biogeochemical dynamics that happen in open water ponds that must have some, that obviously influence how quickly vegetation gets lost at the edges of those ponds and how quickly the pond can deepen and expand. And I know that Giulio's models contain some of that complexity, and there's others who are doing on the field measurements of how what's in the ponds, both substrate wise and just water quality wise, influences the biogeochemistry and how that interacts with the vegetation. But that's definitely an area that is not studied enough, and that's an area that needs a lot more attention.
Yeah, I agree. So the another question by Caroline Curran is, can you comment on model sensitivity to accuracy of LiDAR derived marsh elevations and best approach for correcting data for vegetation interference with bare earth measure?
Yeah, so that's a great question, and that was definitely one of our big concerns when we wrote this paper, and we mentioned it in a couple lines that, you know, this elevation data could have a bias, it could have some error. Unfortunately, the reviewers were okay with that one sentence. And then our first chance to actually do this was in the Chesapeake, where Joel Carr and Kevin Buffington and Karen Thorne produced a DEM that had been corrected using the LiDAR elevation adjustment with NDVI method, the lean method. And so that's what's being shown here. And so I was really happy to see that the overall relationship of UVVR to elevation did not change. You can see that the elevation range compresses quite a bit. So you go from 0 to about 0.6 in elevation of the marshes. And this is basically, if you know the area, this is from Blackwater down to Tangier. Well, it's in this, yeah, it's the left, not including the Delaware, Maryland coastal bays up top, but everything on the western side there that's in boxes. The elevation range compresses to about 0.1 to 0.4 for the most part. So that correction basically shrinks it in. This is the first chance we've had to work with that data. So I'm glad to see that it doesn't really change any of our ideas. The lean method appears to be pretty good. I know that Kevin Buffington is working on a method that does not require the NAIP imagery to do NDVI. It actually uses the LiDAR point cloud to do that correction. And I think that's being written up right now and published. But from what I've seen, there's a lot of ways to do it. The lean method appears to be the only one that's been consistently applied across lots of regions and kind of systematically tested. And I'm biased because it's the USGS, and that bias is because we published those data and we published those methods with metadata, whereas the other methods that I've seen are not things you could readily reproduce or actually query the metadata or the data set and reproduce yourself. So I'm biased towards anything that comes out of the USGS just because of the tracking of those methodologies. So with that, I think the new method is called, I want to say it's called LEAP, LiDAR elevation adjustment with point cloud. So you can keep an eye on that. That should be forthcoming.
Interesting. So one of the last question. So it's
I've got nowhere to be. I'm just here at home all day.
Yeah, but you have no idea how many messages I have here in the chat. But I will take some of them.
Sure.
And try to do it before noon. So this is from Ming Li. UVVR and elevation are a great way to organize the marsh regime. Other factors like tidal range, waves are known to affect marsh. Are these factors folded into these other parameters, or what are potential limitations in this approach?
Yeah, great question. So for the Chesapeake, for example, we will be integrating those other parameters. And actually, at some point we need to reach out to the modelers in the region to apply some of the model outputs to these marsh units. And we've done that in other places. So I don't want to try to share a live demo, so I won't do that. But if there's at least a map, but well, there's no map here of the area. Well, here's the map. So in New Jersey, in Barnegat Bay, we did such a thing where we basically brought in elevation, UVVR, wave attack, salinity exposure, sediment supply, contaminant exposure, and basically mapped all of those variables onto these units, and then computed a vulnerability index and looked at the spatial patterns of that. And that was I want to say that was that might have been 2019 paper. It was in PLOS One. Zafir was the lead author on that, so you can search for that easily. Well, it's on the coastal wetland synthesis page as well. But that's what we plan on doing for the Chesapeake. And we have a list of, I think Zafir and Alfredo and Kate are kind of compiling data layers that we can apply to those marsh units and looking at what's readily available, what's already published, what we can extract from existing models and remote sensing products. And we plan on doing the same kind of vulnerability analysis for the Chesapeake. And the other variable we'd like to bring in that Grace Molino developed is that marsh forest transition likelihood, with the idea that of all the units, for example, I guess I don't show the Chesapeake, but for example, like, here in Assateague, if you can imagine if you had a marsh unit that's right against a forest and it has a very low slope, you could give it a score corresponding to that slope that says, okay, the likelihood for transgression here is high, and include that in the vulnerability index. And that's something we plan on doing as well.
Yeah, really interesting. I saw yesterday the talk by Grace, and it was really interesting. So this is one of my questions. I should ask Grace yesterday, but I think it's related to the UVVR, because when we worked in the mangrove world in the Mekong, we had we started with analyzing vegetated versus unvegetated too. And but when we arrived there, we found like some part very vegetated was not like a mangroves, it was like a nipa palm, something that was even greener than so sometimes I'm thinking like ecological is really hard to discriminate different species from the Landsat image.
Right.
So, but it's I guess it can be because I saw yesterday the talk by Grace showing like the marsh migrating into the forest. So, but if you analyze with the UVVR two different forest and marsh, it's probably a little bit different. So
Yeah, another analogy for that is salt marsh encroachment on, or I guess mangrove encroachment on salt marshes
yeah,
in the southeast, for example. Yeah, and for that, you got to bring in other data products. So you have to bring in, frost, the days of frost, for example. But again, there's a lot of good remote sensing products or spatially complete products that you could bring in along with these data to look at. For example, if you have and this is just again for the southeast, if you have a marsh unit with a very high UVVR, and it's in an area that's rapidly having climate change where there's less frost days, potentially that's an area for optimal, mangrove colonization, for example. So you have to overlay. If you want a full picture, you need many data streams. You can't get it with just UVVR elevation. Absolutely.
so I have another couple of questions. One from James Burgard. When assessing vegetation at each study sites, were transects part of the methodology? If so, how were location for transect lines identified?
Yeah, so for this work, the only field work that's done is the sediment budget work in the tidal channels, which again was the early on work that's shown. I don't have the details. I didn't cover the details of it in this talk, but basically, every dot here that's on the y-axis, the sediment budget was an in situ hydrodynamic campaign for several months to a year inside a tidal channel. There's no on the marsh work. This is all seaward of the marsh, so you're kind of integrating everything that happens. The only transect work that we're involved in for this would be, for example, Grace's work on the marsh forest transitions, where she ground truthed her remote sensing estimates with transects that Joel Carr and Glenn Guttensbergen had put together. And I'm not an expert in how that's done, so I'd encourage you to send an email to Joel. That's Joel Carr, C-A-R-R, who's at the USGS, if you want advice on how to set up transects.
Good. So another question by Michael Team. So when considering UVVR, how would you account for natural disturbances such as hurricanes and their increasing intensity affecting predictions?
Yeah, that's a great question. So that's something we saw, for example, in the Landsat data. And so, I'm sorry, this is going so fast for your eyes. So for example, that Everglades case, and I wonder if I can try to make this bigger here. Well, I won't. But so this is the Everglades, right? And then Flamingo is down here. And we have 5 years of Landsat data for UVVR. And the data showed a sharp change after the numerous hurricanes that hit after 1 year of all of these mangroves being lost. So that was known on the ground from field work. And then the Landsat UVVR confirmed it. So clearly the signal of episodic events shows up in the UVVR. So the question is, what does that mean? So I have a couple ideas, none of which are, justified by any logical thinking, but just my thoughts. And this has actually been published in other papers as well, that the more variability you see in cover, for example, is kind of a metric for both how vulnerable the area is, but also how resilient it is. So it's kind of confusing, right? Because it's both directions. If that area keeps rebounding every time, then it's very resilient. But if it keeps getting hit, then it's also very, very vulnerable. And I don't know what that means from a management perspective. I think from a data perspective, it means that you have to account for that variability and produce that as a metric as well. So you need a trend metric that shows how variable an area is, how stable it is, in order to make decisions with it. So that's why for this Landsat data, we produce an annual product, but we're also producing a composited product over the 5 years along with the standard deviation of those 5 years, so that you can easily see which areas are more susceptible either to high tides that have influenced the imagery, or annual changes because of dieback from salinity exposure or wind or whatever. So that's a great question, and that's why I really think, as a federal government agency, across agencies, we need to have kind of consistent programs that do these mappings on a regular basis, so we can actually look at trends and know what is robust and what isn't. But you're not going to know that without regular updating.
Yeah. So another question by Dong Liang. I wonder whether UVVR has an application for SET monitoring.
SET monitoring, as in elevation monitoring across the marsh?
Yeah. I guess so.
Yeah, I mean, I guess, they're basically two. I mean, that's really the elevation versus UVVR data is that, I mean, they're independent, but they're clearly correlated. The higher your elevation, the more likely you're to be laterally intact. And the lower your elevation, the more likely you are to be laterally unstable, which was in that, we had a discussion about that in that most recent paper, the 2020 paper. The issue, I think, between the two is they're very different also in terms of how they integrate over space and time. So an SET gives you a very rich temporal record of a point, whereas the Landsat or Marsh, the NEIP imagery version, or any imagery really, is a more spatially integrated snapshot over one point in time. So in an ideal world, you have perfect satellite coverage, every 15 minutes. Or in a perfect world, you have an SET that gets read every 15 minutes with 1,000 points on a 1 acre marsh, right? So they're very different measurements, but they need to be brought together and synthesized, which I think is what we're attempting to do here with this work, is trying to bring them together and show that you need both over consistent spatial and temporal scales to figure out what a marsh is doing and how to prioritize investments.
Okay. So we have about 4 or 5 questions. I'm sorry if I'm not, reading all of them, but we are close to we are at the end actually. And
you need to read faster.
Yeah. Well, probably,
maybe I could talk. I'll talk less. Go.
Yeah. I think they can just email to you, because I think they can find your email, and
That's right.
Those are all good questions, but there are several of them. And thank you, Neil. Thank you very much. It was a great talk. I think there are a lot of compliments here too about your talk, and thank you all for participating. And we hope you can join the next one. This is in December 16. Marsh resilience under climate change management and adaptation. It's by Molly Mitchell from WIMS. So thank you very much, and thank you, Neil, again, and see you soon.
Take care, everyone. Stay safe.
Bye.